Today we are going to talk about another generalized Borel Cantelli lemma without the independence requirement. And before that, we shall introduce the following lemma. This lemma is called the Chung Erdos inequality. Let omega A P be a probability space and let A sub case, where k is from 1 to n, be a sequence of events. Then we have the following inequality. The probability of the union of those events, k from 1 to n, is bigger or equal to this quotient. In the numerator, you get the sum from k to 1 to n of the probabilities of this case squared. And in the denominator, you get a double sum ik from 1 to n of the probability of ai intersection ak. This inequality will be called the Chung Erdos inequality. And now let us give a proof. The proof will just be a smart application of the Cauchy-Schwarz inequality. To use the Cauchy-Schwarz inequality, there are supposed to be functions. Now, what function can you think of from the statement of this lemma? It shouldn't be hard for you to consider the following functions. So let x sub k to be the indicator function on a sub k, where k is from 1 through n. Now we consider the integral, namely, in this situation, the expectation of the sum of those functions squared. Let's play a small trick on this. Because if you look at the definition of s sub k, the sum of those functions are actually supported on the union of those events. So this integration will be same as the integration of the product of those two functions. The first guy is the indicator function on the union of those events. And another factor is this sum. And don't forget about the square. And those two parts will play the role of two functions as in the Cauchy-Schwarz inequality. By Cauchy-Schwarz inequality, I should be careful in here. So the Schwarz in here should be a mathematician whose name is without T, and that should be different from the Schwarz who developed the Schwarz space. So, by Cauchy-Schwarz inequality, the square of this integral of the product of two functions is less than or equal to the product of two integrals of squared functions. Now, let's simplify those stuff. Now, let us simplify both sides. First, let us look at the left-hand side. The left-hand side is equal to, by the linearity of this integration, the summation from k equal to 1 to n of the expectation of those indicator functions squared. And this is the sum from k to 1 to n of the probability of a sub k's squared. How about the right hand side? This guy is simply equal to, now going to be very, very careful about this square. This square is on this function, not on this whole integral. And if you think very, very carefully about this, this is simply equal to the probability of the union of those events. You are not supposed to take the square. So let me give you a warning. There's no square, just this probability. That is because a square of an integer function is just itself. So, now let's look at the second term. This guy will be equal to, now let's break down the square of this sum. So you will get the summation ik equal to 1 to n of x sub I times x sub k. And by linearity of the integral, you get this double sum of the expectation of those random variables. And this is equal to simply because the product of two indicator functions is same as the indicator function on the event a sub I intersection a sub k. So this will be equal to the probability of a sub I intersection a sub k. And finally, if you plug in those three guys back to this inequality, you will get the Chung Erdos inequality right here. Those three terms are precisely those three terms. And we are done.